Welcome to the Basics of Sampling Theory, where we explore the fundamental concepts of statistics, population, random samples, and population parameters. Statistics is the science of collecting, summarizing, and analyzing data. Descriptive statistics help us understand data through measures like mean and standard deviation, while inferential statistics allow us to make predictions beyond the data we have. For example, a restaurant collects survey ratings, 1 to 5 stars, from 200 customers. They report that the average rating is 4.3, 70% gave 5 stars, and the range is 2 to 5. This describes the feedback of those surveyed customers but does not generalize to all future customers. To be able to generalize beyond the sample, you need to use inferential statistics. Inferential statistics. Inferential statistics use a random sample to conclude the population. Typically, it is not practical to obtain data from every member of a population. Instead, we collect a random sample from a small proportion of the population. From the sample, statistical procedures can infer the likely properties of the population. Inferential statistics is about making predictions from our data. Here, the goal is to take just a small piece of information, analyze it carefully and then see what conclusions we can infer about the bigger picture. This part of statistics is one of the most powerful and it allows us to find even more information from the data we have already collected. By analyzing a small piece of data, we can infer broader insights, making it a powerful tool for understanding larger trends. Population. In statistics, a population is the complete set of all objects or people of interest. Populations can have a finite size but potentially very large size. For example, all valves produced by a specific manufacturing plant, all adult females in India. If we keep tossing a fair coin, the set of all possible outcomes, T, is finite, but the number of tosses can go on forever. So the population of all possible tosses is infinite. The number of customers arriving in a shop can, in theory, be unlimited. Hence, the population of possible arrivals is infinite. A population is considered to be known when we know the probability distribution f, x, of the associated random variable x. If, for example, x is normally distributed, we say that the population is normally distributed. Random sample. A sample is a subset of the entire population. A random sample is a subset of a population chosen in such a way that each element of the population has an equal and independent chance, probability, of being selected. Key properties of random sample. Unbiased. No element has a better or worse chance of being chosen. Independent. Choosing one element does not affect the chance of another. Representative. If sample size is large enough, the random sample reflects the population. Classroom example, suppose there are 100 students in a college. If we write their names on slips of paper, mix them well, and pick 10 slips at random, that's a random sample. Survey example, a researcher wants to study eating habits in a city. She uses a random number generator to pick 500 phone numbers from a directory. Each person in the city has the same chance of selection. Sampling with replacement, SWR, after selecting an item from the population, we put it back before selecting the next item. So, the same element can appear more than once in the sample. Each draw is independent. This is called sampling with replacement. Example, suppose a bag has 5 balls numbered 1 to 5. If we pick a ball, note the number, and put it back before the next draw, that's with replacement. Possible sample of size 3, 2, 4, 2, right pointing arrow ball number 2 got selected twice. 7. Sampling without replacement, SWOR, after selecting an item from the population, we don't put it back. So, the same element cannot appear again in the sample. Each draw is dependent, since the pool shrinks after each draw. This is called sampling without replacement. Example, same bag of 5 balls. If we pick a ball, note the number, and do not put it back, that's without replacement. Possible sample of size 3, 2, 4, 5, right pointing arrow all different. Comparing sampling with and without replacement, we see differences in pool size, element repetition, independence, and typical use cases. Population parameters. A population in statistics refers to the entire group of individuals, items, or data we are interested in. A parameter is a numerical value that describes a characteristic of the population. Since we usually cannot study the whole population, too large, costly, or time-consuming, we estimate parameters using sample statistics, we'll read later. Common population parameters. Population mean, mu. It is the average value of all elements in the population. Example, the average height of all adult women in India. If we measured every woman in India, the true average height, say mu equals 154 centimeters, is the population parameter. Population proportion, P, it represents the proportion of individuals in the population with a certain characteristic. Example, in an election, suppose 60% of all voters in a state support a candidate. That 0.60 is the population proportion parameter. Population variance, sigma squared, and standard deviation, sigma, variance, measure of how much values deviate from the population mean. Standard deviation, square root of variance. Example, if exam scores of all class 10 students in a country have sigma equals 10 marks, it tells us how spread out their scores are. Population median, mode, percentiles. These are also parameters if calculated from the whole population. Example, the median household income of all families in India is a population parameter.